Welcome back to lecture 20.1, where we're going to continue our discussion of the temperature dependence of the entropy. Okay, so last time in lecture 19, we continued our discussion of entropy. In particular, we covered the TS diagrams, the third law, and the temperature dependence of the heat capacity. Okay. So remember. So by the way, this we are covering in Fin. We're covering chapter 5, but we're also covering chapter 11. Chapter 11 is about the third law. So all of our content about the third law is sitting there in chapter 11, which I believe is 12 in the Rex version. Okay, so remember last time we stated that we had a problem when we looked at the heat capacity of an ideal gas, right? The heat capacity of an ideal gas was constant, right? Heat capacity of ideal gas was constant with temperature. Remember, it just had to do with whether or not it was a monatomic gas or a diatomic gas. And so then if it was a constant, you could take it out of the integral. So we had, for example, S was the integral of C dt over T. And we took the C out of the integral, dt over T. And we said that this gave us this logarithm, right? And that as T F goes to 0, our entropy would go to infinity, right? So there's a divergence in entropy as T goes to 0. And this is clearly a problem, right? So we said instead that, we can't have an ideal gas as T goes to 0. This means that we just basically cannot have an ideal gas, and instead we need to turn into something where the heat capacity will vary with temperature. Okay. All right. So we talked about how if we looked at the heat capacity versus temperature for a metal. So this was for metals. This would be linear in T, proportional to T. So the heat capacity for an insulator should go as T cubed. And we talked about a superconductor which had an e to the minus delta T superconductor. And we mentioned how a metal actually should be okay, right? So if we have a heat capacity that depends on temperature, we should be okay. But we actually transition into a superconductor anyway. So I briefly want to take that idea and look a little bit more carefully at it. Okay, so let's write out our heat capacity again. So our entropy, which is going to be Cp of T dt over T. So let's imagine that our heat capacity is going to have some temperature dependence, which we're going to call, let's say, T to the X, right? I don't know exactly what it is, but let's look at how this power depends. All right, so this is T to the 1, this is T cubed, and let's ask, which one of these should be okay as the temperature goes to 0. Okay, so let's put in this temperature dependence T to the X dt over T, which is the integral of T to the X minus 1 dt. And you can see that if X is greater than 1, right, we're going to have some temperature dependence. So as T goes to 0, so this is going to be like in the numerator, right? So as T goes to 0, then the S will go to 0. That's great. That's consistent with our third law. As, let's say, TF goes to 0. Let's make it give it some actual. Now, if X is less than 1, then S is going to diverge some as TF goes to 0. And X equals 1 is right on the edge. Okay? So the linear temperature dependence is right on the edge of being consistent with the third law. So a metal is okay, except so I have this personal pet theory that this is the linear temperature dependence for most metals is actually slightly less than 1, right? So the very best conductors, copper, gold, silver, platinum, don't go superconducting, right? But most others on the periodic table, tin, lead, mercury, niobium, zinc, aluminum, indium, cadmium, tungsten, titanium, hafnium, like anyway, lots and lots and lots of, they all go superconducting. So even though their heat capacity should be, the temperature dependence of the heat capacity should be okay, it's in fact not. So, okay, so that's good. Now let's take and do an example in class. So we're going to do an in-class example where we're going to calculate the delta S for a particular delta T for a real metal. We're going to do copper. Okay? All right, so in class we'll do that calculation, and then we'll come back at 20.2, and we'll talk a little bit more about the third law.